Section 10.4, Attractive Forces in Compounds. Video problem 54 and 55 follow this, so make sure you watch those. Now when we're talking about attractive forces in compounds, we're typically talking about what are called intermolecular forces. Okay, sometimes they can be called interparticle forces, but we're usually talking about covalently bonded compounds here. So we're talking about covalent molecules, and we're talking about the forces between two different molecules. So in other words, molecule A comes up to molecule B, and how do they interact? All right? Now, these are huge. Intermolecular forces are gigantic. They explain a lot of why things happen. So it's really important to understand this information. All right, so we have the attractive forces between two different molecules. That's going to determine its physical properties. All right, if we have a strong force of attraction, that means we're going to have a high melting and boiling point. Okay, now let's talk about why real quick. So here's a solid. Imagine that this is a solid, okay? And if we want to make that melt, what we need to do is we need to separate the molecules, right? So if we're going to separate the molecules, if we're going to separate these molecules, what's holding them together? Well, the thing that's holding them together are intermolecular forces, the forces of attraction between two different molecules. That's what's holding them together, right? Not covalent bonds, not ionic bonds, just forces of attraction between two different molecules. If those forces of attraction are really strong, it's going to take a lot more energy to get them to separate. All right? All right, and we'll talk more about that in this chapter as well. Okay, so there are three types of attractive forces between particles. Now remember, this is between particles, not within. Within particles, there's a covalent bond, there's an ionic bond, and then we also have metallic bonding. Now, the first force of attraction that we're going to talk about is what's called a dipole-dipole attraction. All right? Now, if the molecule is polar, it exhibits dipole-dipole attraction. How does that happen? The positive end of one molecule is attracted to the negative end of a different molecule. And again, this exists in all polar molecules. So if it's polar, it has dipole-dipole forces. So here's hydrogen chloride, HCl. The chloride is very, very electronegative. The hydrogen is not so electronegative, and so the electrons hang out around the chloride more so than around the hydrogen. This creates a partial negative side and a partial positive side. Well, here comes another hydrogen chloride. And that hydrogen chloride is also as a partial positive and partial negative. And so what happens is that this partial negative is attracted to this partial positive. And that is what's called an intermolecular force between two different molecules. Now we typically show an electronegative force with dots between the molecules, just like that. All right? And so this particular intermolecular force is what's called a dipole-dipole force of attraction, or dipole-dipole attraction. Again, it happens in all polar molecules, and you can see why, because all polar molecules are going to have a positive end and a negative end. So all polar molecules are going to line up such that the negative is going to be attracted to the positive. Now, as you increase temperature, that lining up changes, and again, we'll talk about that. Now, a special type of dipole-dipole bond is what's called a hydrogen bond. Okay, so this is a special type of dipole-dipole, and the reason why it's a special type is because these are incredibly polar molecules, polar bonds. All right, this happens whenever a hydrogen is directly bonded to a nitrogen, oxygen, or fluorine. Okay, so when you have a hydrogen bonded to a nitrogen, oxygen, or fluorine, you have a hydrogen bond. It's really strong. The reason why it's really strong is because you're talking about a hydrogen, okay, which is a fairly small particle. being directly bonded to another fairly small molecule, but it has a really, really large nucleus compared to the hydrogen. And so it can really pull those electrons over, which creates a very large dipole, very large polar bond. Now, important, the actual hydrogen bond is between two different molecules. So here's a hydrogen, and that hydrogen is bonded to the nitrogen, right? So that means this molecule has the opportunity to exhibit hydrogen bonding. But the hydrogen bond is actually between the hydrogen and a different particle's nitrogen. Okay? Now let me show you something here real quick. Here's methane, CH4. Methane cannot exhibit hydrogen bonding. Why? Because the hydrogen is not bonded to a nitrogen, oxygen, or fluorine. It's actually bonded to a carbon. So there's the first idea. Let me show you the second idea here. Let me get this in here. So here's a molecule. All right. Again, notice the hydrogen is not bonded to a nitrogen, oxygen, or fluorine. So this molecule cannot exhibit hydrogen bonding. But if I bring a water molecule up close to this, a water molecule can, let me draw that differently, sorry. Water molecule can exhibit hydrogen bonding, right? Because the hydrogen is directly bound to a nitrogen, oxygen, or fluorine. So here's something that can show hydrogen bonding. Here's something that can't show hydrogen bonding. But remember, the hydrogen bond is between two different molecules. So this hydrogen will actually form a force of attraction with this other atom's, or other molecule's oxygen. So that is a hydrogen bond force of attraction. Okay? So it's between the hydrogen that's bound to an oxygen with a different molecule's nitrogen, oxygen, or fluorine. And actually more research is coming out to say that this is a little more expansive than what we currently name it, but we're fine with what we're talking about. Now, the hydrogen bond is a really, really strong force of attraction. Okay, it's still relatively weak compared to covalent and ionic, but it's relatively strong compared to the other types of intermolecular forces. So far we have dipole-dipole force of attraction. We have a hydrogen bond force of attraction. The final one is a dispersion force, or what is often called London dispersion force. Okay? Now these are relatively weak, but they are huge and important. They play a very important role in molecules and in the macro structure. So like I said, they are weak but very important. They occur between both polar and nonpolar molecules. So in other words, if it's a molecule, it has London dispersion forces. Now, these occur because of constant movement of the electrons, and basically at one instant, there's going to be more electrons on one side than on the other. So take a look down here. I'm going to label these atom A and atom B. Now, this is a nonpolar molecule. All right. So you can see in molecule A, the electrons are distributed fairly equally. In molecule B, the electrons are not distributed equally. So what happens is the electrons are on one side more so than the other. So this becomes negative, this becomes positive. So as soon as this becomes positive, this atom is going to change. So atom A now, since this side was positive, the electrons are attracted to that positive side, means the electrons move over to the other side, which creates a partial negative and partial positive charge there. Now we call this a temporary dipole because the electrons are free to move about. But once this forms, there's this force of attraction. So that's the London dispersion force. But as soon as it forms, remember those electrons are free to move about. These electrons can move back and completely make that dipole disappear. All right, so it's gone. Then the molecule next to it will do the same thing. I often say that this is similar to the wave. So when you go to do the wave, you know, you stand up, you put your arms up, and then whenever you go to sit down, so you go to sit down, the person next to you puts their arms up, right? And then whenever they go to sit down, the person next to them puts their arms up, and so on and so forth. So what happens is you create a partial dipole or a temporary dipole by standing up. And when you do that, that induces the person next to you to stand up. But then you sit down immediately, and then they sit down immediately. So they go back to being nonpolar. But it continues throughout the molecule. And that's a London dispersion force. Okay, now here are some other forces, and I want to mention one particularly. So this is going from strongest to weakest. The ionic bond we say is the strongest. The covalent bond is next. And then hydrogen, dipole-dipole, London dispersion force. Now there's another one that is called an ion dipole force. Okay, it's not in the notes here. An ion dipole force is between an ionic compound or an ion. Let's say it's a positive cation, right? And then here's a dipole or a polar molecule. Let's use water because we always use water, right? So what's going to happen? Well, when this positive comes up close to this molecule here, the negative is going to be attracted to that positive. So if I draw, here's the next picture. Here's the cation, here's the oxygen. That partial negative is going to be now pointed towards that cation, and we're going to form a force of attraction. So let me draw my little dots in there. There's the little dots showing the force of attraction, and then another water molecule is going to come over here, and this is what's called the solvation process. Okay, this would be dissolving ion a compound, and then again we have this force of attraction. Okay? Now the result of these forces of attraction are basically why we have different physical properties. Okay? So couple things you want to know. These are a couple guidelines. As the mass of the compound with similar attractive force increases, the boiling point increases. And when you know, it's not a bad idea to go and look at those video problems now. Stop this video, go and look at the video problems, and come back to this. So as the mass of the compounds with similar attractive forces increases, the boiling point increases. In other words, if I have a dipole-dipole molecule and another dipole-dipole molecule, which they have, they also have London dispersion, because every molecule exhibits a London dispersion. So we would think that they would have similar intermolecular forces. We would think that they would have similar strength, but they don't. And the reason why they wouldn't is because of the number of electrons. The more electrons you have, the stronger that London dispersion force. The stronger the London dispersion force, the stronger the overall molecule. Okay? So what does it matter? Why does it matter how strong that force is? Because in order to boil or melt, the molecules must be separated from each other. In the case of boiling, they have to be completely separated. In the case of melting, they just have to be weakened. The forces of attraction between the molecules have to be weakened. Okay? And so that's what I'm saying here, done by breaking the forces of attraction between the molecules. And again, we can weaken them as well. Break-in or weaken, and that would be like melting. So, and here's where I get into the number of electrons. So the molecules with similar attractive forces will have different boiling points, and it's all because of the relative strength of that London dispersion force. So here's the reason. More electrons means more strength. And we can figure out which one has more electrons by looking at the mass. But very important, it's not correct to say the greater the mass, the stronger the London dispersion force. That's not true. It's the greater the number of electrons, the stronger the London dispersion force. So again, making sure that you give the reason, the correct reason for the observation is important. So the stronger the dispersion force, the higher the boiling point. And really what we want to say here, when we're talking about more electrons, we say that the more electrons, the more polarizable it is. Okay? So the more electrons, the more polarizable. So what does that mean? Well, what that means, more polarizable means that the more electrons we have, the greater the chance of it being polar. Okay? Think of an atom with 2 electrons, or a molecule with 2 electrons. We have 2 electrons on one side. So here, let me draw this out. So here's this. Right? Here's the middle. So we can have 2 electrons on one side. That's polar. We can have 2 electrons on the other side. That's polar. And then we can have 1 and 1. right, which is nonpolar. So there's two chances to be polar, one chance to be nonpolar. Now imagine, let's say, 50 electrons, right? So with 50 electrons, I can have 49 electrons on one side, 1 electron on the other. That's polar. 48 and 2, 47 and 3, 46 and 4. You can see now I'm getting a lot more opportunity to be polar because I have more electrons. Greater chance of being polar means it's more polarizable. Okay? So here we can see with these organic alkanes, right? We've got a CH4, which only has a handful of electrons, has a boiling point of negative 162. In other words, it's pretty easy to make that change from a liquid to a gas. Right? It doesn't take much energy at all, negative 162 degrees Celsius. Ethane, a little bit bigger, so more electrons, has a boiling point of negative 89, so it takes more energy. Skip up to butane. A lot of electrons, takes a lot more energy to make it turn into a gas. Why? Well, first of all, these are nonpolar molecules, right? Because the carbon-hydrogen bond is nonpolar. So these are nonpolar molecules, which means that they only have London dispersion forces present. With only London dispersion forces, then we're comparing all of these. We're comparing all of these based on just one intermolecular force, London dispersion force. More electrons, the more energy it takes because it's stronger force of attraction. We can also take a look at the melting point, okay, where it goes from a solid to a liquid. And again, just very, very similar. A compound with weak attractive forces will require less energy to separate the molecules, and they'll have a lower melting point. The stronger attraction requires more energy to get them to separate, therefore a higher melting point. And again, we can be looking at the number of electrons. So let's take a look at right here. These three, okay? We have hydrogen iodide, Hi. We have hydrogen bromide. And we have hydrogen chloride. All right? Now these aren't aqueous, so we're not going to call them acids. So it's just hydrogen iodide, hydrogen bromide, and hydrogen chloride. Now we can see there's a huge difference, right, in melting. Why? Well, they all have similar intermolecular forces. They're all covalently bonded, but they all have London dispersion dipole-dipole because they're all polar molecules. So in other words, they all have the same types of intermolecular forces. London dispersion has a certain amount of strength. Dipole has a certain amount of strength, so they're all three sort of matched up. So why do they have different melting points? The reason why they have different melting points is because the number of electrons, right? Hydrogen iodide has the most electrons. Hydrogen chloride has the least electrons. So more electrons means more polarizable. More polarizable means stronger London dispersion forces. And the reason why it's stronger is because it's quote-unquote turned on more often than it's turned off. So if you can easily polarize, that means you can easily form that temporary dipole, which is turned on. And you're going to do that more often. So you're going to be turned on. That London dispersion force is going to be turned on more often with more electrons. Okay? Go on over to the video problems, and that'll give you some more examples of what we're talking about.